With the start of Unit 4, we are going to focus on two specific types of functions, polynomial functions and rational functions. The majority of this unit is going to be focused on polynomial functions, and that's where we're going to jump in today. So in section 1, we are looking at polynomial functions, but more specifically, a specific type of polynomial function. It's kind of like if polynomials were dogs, we would be looking at a bulldog. It's a specific type. So a quadratic function is a polynomial, but we're only going to look at quadratics in this first section. So the objectives, we're going to recognize characteristics of parabolas, we're going to graph them, and then we're going to do an application problem. So when I talk about quadratic functions, remember something is quadratic if it's in this form. So the thing that makes it quadratic, the highest exponent is a 2. When we graph quadratic functions, the shape that comes out, you can see them down here, they look like U's. That shape is called a parabola. So if you hear me use the word parabola, I am referring to that shape. And another important vocab word that we're going to be dealing with, when I look at these parabola shapes, the very bottom of it, or the very top of it, that point, is called the vertex. So the vertex of the parabola is either the lowest point on the graph or it's the highest point on the graph. It depends on if the parabola is opening up or down. So on this left one, it's the lowest point. On the right one, it's the highest point. There is an imaginary line that will always cut the parabola right down the middle, whether it opens up or down. And this imaginary line that cuts it into equal sides, that is called the axis of symmetry. And you can see it labeled on your picture, but I want to go through it again down here. So the vertical line that goes right through the vertex, and it divides the parabola into two equal portions, that is called the axis of symmetry. Now you might ask, what is the purpose of the axis of symmetry if it's technically not even there? You wouldn't even see it if you're looking at the parabola. Well, it goes back to the fact that mathematicians, we like shortcuts. So if I was graphing a parabola, and let's say my vertex was right here, and then let's say I had another point right here, well, if I know that I have the axis of symmetry right through the vertex, it speeds up the process because I know if the left half looks like this, then in theory, the right half has to be a mirror image. So it's a useful tool to speed up the graphing process. If we know what one half looks like, we know what the other half is. So it is useful to be able to find out where is that axis of symmetry. The equation of the axis of symmetry will always be in the form x equals a number because it's a vertical line. And the number is the x-coordinate of the vertex. And we'll do an example with that. The other thing that you want to know, the vertex itself, when we're talking about its ordered pair, they use the letters H and K to represent the ordered pair of the vertex. Why those letters? I don't know, but those are the letters they've decided. So if you see H and K mentioned, that's going to be like the lowest point or the highest point. And finally, one other shortcut that we'll want to be on the watch for, and then we'll try examples. How do we know just by looking at the quadratic if it's going to open up or down? Well, again, if we're in this, I'll write it down here. If we're in this form, ax squared plus bx plus c, you want to look at the leading coefficient, the leading number out front. If a is greater than 0, so if a is positive, think happy parabola. That's a mess. It's going to open up if a is positive. If that a is negative, if it's less than 0, think sad. The parabola is going to open down. That will always work. So when we go to graph these, one form that the quadratic might be written in is called standard form. So standard form is a and then parentheses x minus h squared plus k. It may look intimidating, but I'll tell you this is the easier form to work with. So the steps to graph a parabola. Step 1, you want to determine, is the parabola going to open up or down? And what I was just telling you, you want to look at a to decide that. So if a is greater than 0, we're going to open up. If a is less than 0, the parabola will open down, always. The next thing you would want to know about the parabola is its vertex. And remember, the vertex is going to be the letters h and k. So whatever is sitting in h and k spot is the vertex. Step 3, we're going to find the x-intercepts, and we'll go over how to do that. Step 4, we're going to find the y-intercept. And then step 5, we're going to tie it all together, and we're going to plot everything and make our graph. So let's try an example. So they give me this quadratic. I know it's quadratic because the highest exponent is a 2. So the first thing let's decide is this thing going to open up or down? Well, look at a. A is negative 2. Because a is negative, I know this parabola is going to be opening down when it comes time to graph. The next thing I want to know is the vertex. And remember, the vertex is hk. H is with the x, k is out back. Now, be careful if you think of what we did when we did the transformations unit. I said the number inside with x was always a liar, and that still holds true. So the vertex would actually be positive 3, 8. H is a liar. So there's my vertex. The axis of symmetry, this imaginary dashed line that will cut my graph right down the middle, it's going to be x equals, because it's a vertical line, and it has to go through the vertex, so you literally use the x-coordinate of the vertex. Okay, my x-intercepts. If I want to find the x-intercepts, remember that's where the graph crosses the x-axis. So to find the x-intercepts, you put 0 in for y and solve for x. Because I want to know what is x when y is 0. So let's go through this. If I wanted to solve this, I would have to subtract 8 over first. And then what would I do? Well, I would get rid of this negative 2. Since it's connected by multiplication, I'm going to divide it. And now what you could do, you could FOIL this right side out, or since that entire side is squared, let's just square root it to cancel the square. So 2 equals, and now I just have x minus 3. Now you should be yelling at me because we took the square root. So remember, plus minus needs to appear with the 2. And the last step would be to add 3 over. So to get my two x-intercepts, 3 plus 2 and 3 minus 2. So I get 5 and 1. Those are my two x-intercepts. If I want the y-intercept, that's way less work. So if I want to know where does it cross the y-axis, this time I put 0 in for x. So if I put 0 in for x and simplify, 0 minus 3 is negative 3. Negative 3 squared is positive 9. Negative 2 times 9 is negative 18 plus 8. I get a y-intercept of negative 10. Okay, and we'll talk about those final three things here once we have the graph. So what I would do, let's plot the vertex. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8. So here's the vertex. I can plot my x-intercepts. So I'm going to touch the x-axis at 1. I'm going to touch the x-axis at 5. I can plot my y-intercept. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, just enough. It's going to cross the y-axis at negative 10. What might also be helpful, let's draw in the axis of symmetry. So it's a vertical line going right through the vertex. And when we draw in the parabola, it should be a mirror image on either side. So I'm going to draw it in. Arrows on both ends to show that it would keep going. So there's my parabola. So now the next thing I asked for, do we have a max or min? Well, we created a hill. So we have a max value. And finally, the domain and range. Domain, remember, are the inputs, so we're looking left and right. How far left does my graph go? How far right? You might be tempted to say, oh, from 1 to 5. But because of these arrows, the graph keeps going all the way left and all the way right. So my domain should be negative infinity to infinity. That will always be the domain for parabolas. Always, 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 always. That is the domain. The range, remember we want to think vertical. How far down does this graph go? Well, because of the arrows, we keep going. So you should say negative infinity. And what's the highest point my graph reaches? Well, it was 8. And I want to bracket because I actually reached that point. Okay, a lot of analyzing, but we're kind of just taking all these pieces that we've used in previous sections and applying them to quadratics. Let's try another one. Oh, fun fact. Look at this. If the parent function was just x squared, which does this, look at these transformations and see if it makes sense. We know the plus 8 would move it up 8. We know the minus 3 would move it right 3. We know the negative out front would flip it upside down. And this 2 is a vertical stretch. And that's how we get this blue graph. So if you think you graphed it wrong, look at the transformations and see if this graph ended up or moved the way that it should have moved. So next one, is this graph going to open up or down? Well, we look at A. Technically, A out front is 1. Since it's positive, I know my parabola is going to open up. The vertex, remember, is HK, but H is a liar. So it should be negative 3, positive 1. The axis of symmetry, this line that would cut the parabola right through the middle, is x equals, because it's a vertical line, and it's the x-coordinate of the vertex. It has to go through the vertex. The x-intercepts To find the x's, I'm going to put 0 in for y. So to solve this, I could subtract 1. And then we're going to get rid of the square by square rooting. So I get x plus 3. Ooh, what's the square root of negative 1? You should say it's I plus or minus. I'm actually going to stop the train there because if I finish solving for x, I have imaginary intercepts. So what that actually means, because they're imaginary, this parabola will not touch the x-axis. It will not touch the x-axis. So let's look at the y-intercept, see if we have better luck. To find the y-intercept, we're going to put 0 in for x. So 3 squared is 9, plus 1, we get 10. So we do have a y-intercept at 10. All right, let's throw this onto the graph here. So the vertex, negative 3, positive 1. My y-intercept, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Perfect, right up there. I'm going to draw in my axis of symmetry right through the vertex. Now, where that's going to especially be helpful is I didn't have any x-intercepts to plot, and that's okay, because if I have the y-intercept, notice how it was 3 to the right of the yellow line. So then I know there's going to be another point 3 to the left, because it has to be the same on either side. That's where this axis of symmetry is helpful. So now I'm going to draw in, ooh, not the best, but make sure you have arrows on either end to indicate it keeps going. There's my parabola. So have I created a max or a min value? Well, because we have a valley, we have a low point. So we have a minimum. Domain, how far left, how far right? Well, it keeps going to the left forever, and it keeps going to the right forever. Range, how far down does this graph go? It does not go past 1. How high up? Infinity. And if you wanted to check if the parent function was just x squared, notice the two transformations. This plus 1 takes it up 1. This plus 3 takes it left 3. Notice my parabola did go up 1 and left 3. All right, there is one other way to graph quadratics, or another form that it could be in, and it's the form that I was talking about at the beginning of the unit. So if I want to graph the parabola and it's in this form, we do have one slight issue. Notice in this form, I can't directly pull h and k because there is no h and k. So we have to find the vertex another way. And to do that, here's how you get the vertex from this form. It's going to be an ordered pair, but it's not h and k. To get the x coordinate, you are going to take negative b divided by 2 times a. This is kind of coming from the quadratic formula itself. Once you have the x coordinate, to get the y coordinate, you are going to substitute in your x. You're going to substitute your x coordinate back in. That's what this means. Hopefully it'll make sense once we do an example. So, on your notes, I believe I changed this. If I didn't, please change it to say 2x squared minus 7x minus 4 is what I want this example to say. So we're going to still identify everything the same way. So the first thing, opens up or down? Well, let's look at A. A is 2 and it's positive. So I know my parabola is going to open up. Now the vertex, this is where it takes a little bit more work because I can't just pull h and k. So to get the vertex, I'm going to do negative b over 2 times a. So b is negative 7. So when I plug it in, I'd have a negative 7. So it turns opposite. And 2 times a would be 2 as well. So if we do that math, we get 7 over 4, which, oh no, it's a fraction, but that's okay. If you want to turn it into a decimal, you can. Hang on just a moment. All right, so if you wanted to write that as a decimal, 7 divided by 4 would be 1.75. I'm okay with that being a decimal because we didn't do any rounding. We didn't have to cut any part of the answer off. So what that means, when I write my vertex, that is the x-coordinate. That's kind of like our h. So now we just need the y-coordinate. To get the y-coordinate, all you do is you're going to plug that value in for x. So I'm going to take 2 times 1.75 squared minus 7 times 1.75 minus 4. You're substituting it back in to see what comes out. So if we do that in our calculator, the value that should come out is negative 10.125, or you can write it as a fraction. Okay, a little bit funky numbers, but it's the same process. The axis of symmetry is still going to be that imaginary vertical line that goes right through, and it's going to go through the x-coordinate of the vertex. To find the x-intercepts, I am going to set my function equal to 0. Now to solve this guy, we're probably going to have to factor it. So I want to multiply to negative 8 and add to negative 7. What two numbers do that? A negative 8 and a positive 1. So if I rewrite it, group, so I can see I get a 2x plus 1 and an x minus 4. And then if I set each piece equal to 0 and solve, I have my 2x intercepts, 4 and negative 1/2. To get the y-intercept, I'm going to put 0 in for x. Oh, my work's kind of all over the place here. So if I do that simplifying, the only thing I should be left with is negative 4. Let's see if we can throw this all onto the graph. So my vertex is 1.75, and then down negative 10, a little bit more. So there's my vertex roughly. My x-intercepts are going to be at 4 and negative 1/2. And my y-intercept should be at negative 4. And again, technically when you graph this, you don't need the x-intercepts, because if you have the vertex, that's where I would draw in the axis of symmetry. And if you have the y-intercept, really all you need is the y-intercept. So like on this one, because it's over, that would be a distance of 1.75, I would just have to go 1.75 to the other side. But since I have the x-intercepts, I'll just use those. But again, just know it's a mirror image on either side of that imaginary line. So it looks like I have a minimum, a low point. My domain should be negative infinity to infinity. And my range, it looks like the lowest I go was the negative 0.125. And the highest I go is infinity. All right, the last thing I want to do is the application problem. A lot of the times when you're dealing with quadratics, especially in physics, is when you're dealing with projectile motion, something being thrown or fired or shot into the air. So the figure below shows that when a football is kicked, the nearest defensive player is 6 feet from the point of impact with the kicker's foot. The height of the punted football, which is f of x in feet, can be modeled by, and then they give me the function, where x is the horizontal distance in feet from the point of impact with the kicker's foot. What is the maximum height of the punt and how far from the point of impact does this occur? All right, so let's think about it here. When he kicks the football, we're going to get a parabola shape. And it's going to be opening down. And to further know that it's going to be opening down, if you look at the function they gave me, the a value is negative. So I know it's opening down. So they want me to find the maximum height. So they want to know, how high does it go? Well, what did I tell you that point was called? It's the vertex. If you can find the vertex, you will have the answer. So because we're in this form, ax squared plus bx plus c, I'm going to have to use the second way of getting the vertex because I don't have h and k. So to get my x coordinate, I have to do negative b over 2a. So if I substitute in, b is 1.18, so it'll be negative 1.18 over 2 times, and a is negative 0.01. If you do that, you should get 59 out. Now, if you don't see that number out, be careful if you're putting this all into the calculator at once. You need to make sure you do this multiplying down here first, and then take negative 1.18 divided by that. So now to get, so that's my x-coordinate of the vertex. To get the y, we have to plug that 59 back in for the x's. So plugging it in, I want to simplify that and see what comes out. So if we enter this into our calculator, I think we have to round this. So we'll go to the hundredths place. I believe it's about 36.81. Okay, but that's not good enough. Now I actually want you to answer their question. So they said, what is the maximum height? So which of those two numbers in that ordered pair represents the height? Well, it should be the y-coordinate. So we have a maximum height of 36.81 feet. And then they did ask another question. They said, how far from the point of impact does this occur? So what they want to know is, when I reach that maximum height, how far have we traveled? Well, we already have that answer. The how far answer is our x-coordinate of the vertex. Okay, and I am actually throwing out this part.